Welcome to Microlecture 23, where we talk about monosubstituted cyclohexane chairs. Okay, so now that you have practiced drawing your cyclohexane chair structures, let's go ahead and think about what happens when we put a substituent on the cyclohexane ring. So I'm going to draw my cyclohexane chair, and I'm going to put a methyl group on it. So in this structure, I'll just put the methyl group upward and axial. I'm going to go ahead and put the CH3 there. And then just for practice, what I'm going to do is go through and put in all these little hydrogen atoms that we know are there. You wouldn't have to do that for any of these structures, just like you don't have to do that in a skeletal structure, but it's good practice for now. So those are all the positions. And so there's this methyl group on one of the carbons, and we want to think about whether this version of the chair or the ring flipped chair is better, or are they the same? And so we're going to go ahead and ring flip our structure. Remember, that means that we're taking the nose that's upward and pointing it downward, and taking the nose that's downward and pointing it upward. And so go ahead and draw that now. And the CH3 group that was up and axial is now going to be up and equatorial. All right, and so those are the two ring flipped structures. So the question is, which one is more stable? And if one of them is more stable, then by how much? How much energy? And so table 4.8 has this information for us. You would be given this information. What happens when a group, an R group, like a methyl, is in an axial position, is that the hydrogen atoms that are coming off of this group are getting close to the electron clouds of the hydrogen atoms that are also in axial positions. And so those positions are at carbon 1. If we call the methyl group a group that's on carbon 1, so if we call that carbon number 1, then move over 2 more carbons to carbon number 3, either clockwise or counterclockwise, and you'll see that you have another axial position. So we call this type of strain 1,3 diaxial strain. So again, this is when any R group is situated axial. And table 4.8 shows the strain that occurs when a methyl group is interacting via 1,3 diaxial strain. So it costs 7.6 kilojoules per mole of energy to have a methyl group in an axial position on a monosubstituted cyclohexane chair. And so what that means is that 95% of the molecules would be in the more stable conformer, which is going to be the one that has the methyl group in the equatorial position. So this will be more stable because it avoids 1,3 diaxial strain, and about 95% of the molecules are in this conformation, and about 5% are in the conformation in which the methyl group is axial. And so as you can imagine, as we get into more bulky and larger substituents, we're going to see a more dramatic effect, and eventually we're going to see for very, very large R groups that the molecule spends almost all of its time with the R group in the equatorial position rather than the axial position. So let's do this example right here. This group is called a tert-butyl group. So let me just draw it out longhand real quick. And that's the same thing as this. All right. So let's draw a tert-butyl cyclohexane chair. And again, that means drawing the chair structure, and then we can go ahead and draw a tert-butyl in the axial position, and then ring flip the chair structure. And the tert-butyl that was upward and axial is now going to be upward and equatorial. All right, and so the 1,3 diaxial strain of having a tert-butyl group in the axial position is 22.8 kilojoules per mole. That's how much it costs. And so almost 100% of the molecules are in the more stable conformation with the large tert-butyl group sitting equatorial.